Hello, everyone. My name is Martin Sopik. I'm a PhD student at ETH Zurich, supervised by Thorsten Hepler, and I'm going to present our work on using program analysis results to improve the workflow of performance modeling. This research has been conducted in a collaboration with Tobias Grosser from the University of Edinburgh and with Felix Wolf from the Technical University of Darmstadt. In performance modeling, we usually consider a high-performance application for which we want to derive a set of analytical models. One model per function. The models are parameterized with program parameters, and they describe the behavior of metrics such as time, the number of instructions measured, or the memory accesses. Usually, we consider just time. The models are used to detect scalability bottlenecks of the application. So before we scale the application on a very large run, we can analyze its behavior and find out which components of the application scale poorly. They can be used to find out whether given a library meets our expectations, such as in the example of MPI collectives, we have theoretical expectations of how should they perform, but also we can performance modeling to verify if the implementations actually follow the best possible algorithm. And finally, when we measure instructions or memory accesses, we can also use those models to design a system that best fits our application needs. The workflow of performance modeling begins with a selection of parameters. We can only afford to model up to 2 or 3 parameters because of the excessive compute time requirements for larger modeling processes. Like in this example, we select problem size S and the MPA ranks, number of MPA ranks at P, which is a typical choice of 2-parameter modeling. Later, the user must select few evaluation points for each sample, at least 5, and we must consider all combinations of those evaluation points. So for 5 parameters, 5 evaluation points per 2 parameters, we get 25 repetitions. The application is instrumented. Our usual choice of instrumentation is Scorpion. To get statistically valid measurements, we need at least 5 repetitions per evaluation point, which gives us 125 executions to run. The results of those measurements are passed to XtraP, which is a state-of-the-art empirical black box performance modeler. It is going to produce analytical models based only on the measurement data. This workflow has few crucial challenges that limit its applicability. First of all, the user already must be an expert to select the most important parameters. Like in the example of milk, we have many different parameters, and unless you really know the application very well, it is very hard to select which parameters have the highest effect on the performance, and also which of parameters might be completely numerical and have no influence on the performance whatsoever. Without program knowledge, it is impossible to determine whether there isn't a multiplicative dependency between parameters. When there is one, we must consider all possible combination of parameter values when doing experiments. Theoretically, we can also use a more sophisticated machine learning-based tools that can reduce the number, like in this example, from 25 to maybe even down to 10, but this also affects the accuracy of measurement. However, if we knew that there is only an additive dependency between the parameters, we could simply don't consider combinations at all. The instrumentation adds a significant overhead, which affects the quality of results and also makes them more expensive. But since we don't know anything about the program itself, we must instrument all functions, even many trivial short time and constant time functions. Since XtraP is a black box modeler, it doesn't know anything about the functions of the program and the parameter dependency. Therefore, it might lead to creating overfitted models with false dependency. Like in this example, XtraP sees a potential model with a very good fit and a false dependency on parameter S, maybe with very low constant, but it cannot remove it because it doesn't know that there should be no dependency on S. And finally, when we get the model in the end, we don't know whether it describes our application or it has been influenced by the specific experiment choice and the hardware we're using. So we have no way to determine whether the model actually describes more the application itself or maybe the measurement data. When we combine all of those 5 challenges, we notice that all of them could be solved by introducing program information to the workflow. Therefore, we must turn this black box approach into a white box one. So let's take a look at what are the exact requirements in our case for a program analysis. In a typical program, we have many different functions that are usually composed, and we have many short running and maybe constant time functions like this one, and we begin by removing all of them. So we want to completely remove from consideration all functions that we know are completely constant. Then we have important functions such as doing maybe MPI communication or other pulse synchronization, and also doing computation. When we have a function in computation, we must be able to determine which parameters affected this. Such as in this example, we examine loop exit conditions, and we have to determine if any of those parameters affected the loop exit conditions. If none of them did, it means that the function is constant. The runtime of the function is constant with respect to our parameters. However, since we may have very nested call stack, it is not trivial to determine which input parameters affect this. So therefore, we must go up to the main function to be able to locate which parameters affect this particular loop. Therefore, in addition to determining performance relevant functions, we must be able to determine which parameters affect their performance. To summarize the requirements, our analysis must be able to detect which functions are constant time, so we don't remove them from consideration. It must provide us with information which parameters affect a given function. It must be interprocedural. It must support arbitrary memory movements, which is extremely common in C or C++ applications. And finally, we must add to the analysis a support for pulse and pattern expressed such as library by MPI. Our answer to this challenge is dynamic taint analysis, a computer security technique originally used to track the propagation of potentially malicious program input through the application. Let's take a look at an example how it works in practice. So on the left side, we see a user code. On the right side, we memory. We already see a significant change. So in addition to the user-defined program memory, we allocate the so-called shadow memory. The idea is that we associate with memory allocation taint labels that describe, in our case, which parameters have affected this given memory location. And through the application, we'll add instrumentation to keep track the propagation of labels during the program execution. So in this example, we begin with the MPI size of the communicator, which is for us is an important parameter describing the size of parallel run. Therefore, in a shadow memory location corresponding to the variable b, we introduce a taint label. This gives us information that this value has been affected by a given parameter. In addition, we expose a function to the user to taint variable parameters by itself, simply because there is usually a configuration routine or maybe main function when the input is read from the user. And this is the place where we want the user to annotate that this is the set of my parameters. Please keep track of them. We add instrumentation to keep track of the labels propagation. So such as in this example, we can simply, when we produce the new value, we propagate 10 labels from the input to the output. So when we produce the new value in a data flow fashion, we also copy the label. Similar thing happens of course, when there are multiple labels, we simply take a union of them. And in addition, we also must keep track of control flow propagation. Simply, for example, when we make a decision that is based on some parameter, it is also going to affect might affect the performance. For example, we might choose a loop size based on a value of specific parameter. Therefore, when we make a control flow decision based on a parameter, we also taint the results affected by this decision. This already gives us an understanding on how we can proceed with the user code. So we can easily taint this. We can keep track of the memory. When the user uses some libraries, we also can compile those libraries as well, adding the instrumentation and also keeping track of the memory. However, the case is not so simple for MPI. MPI are usually have its own internal state, and to understand what happens in this internal state, we would have to compile an MPI implementation. This is not a particularly good idea. For example, it will make it very hard to deploy a tainted application into a cluster, which is kind of problematic. We might want to run a tainted application on large scale, but it becomes extremely difficult when we don't use the standard cluster version of MPI. Our solution to that problem is to simply describe the tainted behavior of MPI. So instead of trying to analyze the library, which is difficult, we simply provide an interface which can also be easily scaled to other libraries such as OpenMP. So an example of such interface for MPI is that we first introduce the taint labels that are defined by MPI. So in this example is the number of MPI ranks P, which is produced by some of those functions. Those become taint sources in our application. So in this example, every time a user queries the size of the communicator, we simply going to add a taint instrumentation for the result value. In addition, we add taint sinks, so places where the labels are consumed. Usually we inspect for loops to understand which labels affect loop exit conditions. But for MPI functions, we add implicit dependencies. So we know that MPI reduce is going to have a performance model that depends on the number of MPI ranks. We cannot analyze this. Therefore, we implicitly add a dependency on P there. We don't specify the complexity class, that's the role of extra P. In addition, since the complexity of this function can also be influenced by the size of the data buffer, we also have to query the performance labels of the specific parameter to get a complete understanding of parameter effect on this function. To summarize, to those two components, we introduce a new tool. We call it PerfTaint, which is a hybrid taint analysis framework. First of all, we ask the user to annotate the source code. So this is one single line of code per parameter, simply to tell us which variables are actually parameters, and we're going to keep track of them. So this is a very low intervention on the user side. Then this annotated source code is propagated, is passed to our tool, which begins with standard LVM passes determining which functions are completely static and which loops are static. This helps us to remove all functions that shouldn't be instrumented at all. Then we add taint instrumentation and execute the application on a selected evaluation point somewhere in the experimentation domain. This provides us with two different types of result. First, we get a list of important performance relevant functions. And for those of them that are actually performance relevant, we get the list of parametric dependencies. So now let's take a look on how these results can be used to improve the workflow of performance modeling. First of all, instead of relying on user expertise to select the most important parameters, we can provide a taint-based coverage. Simply count the number of functions and loop affected by given parameters. This metric can help the user to detect which parameters are actually the one that they should be interested in. When designing the experiment, the user can use their own knowledge or maybe this complex heuristics and tools to reduce the number of samples. However, we might be able to detect when there is only additive dependency between different parameters. Therefore, we can pass this information to improve the performance of experiment design. When instrumenting functions, instead of instrumenting all of them, we can simply skip the constant time functions. And similarly for the modeling, we can, instead of modeling all of them, we can only model those that are performance relevant. To evaluate our tool, we are going to show three classes of results. First, we are going to show that the models can be obtained cheaper by performing fewer and cheaper experiments. We show how the quality of models can be improved by reducing the effect of noise and instrumentation intrusion. And finally, we show how we use the discrepancy between our results and black box results to find out problems in the experiment design. We evaluate benchmarks on PSDaint. It's a Swiss supercomputer. And we also use our in-house cluster to evaluate the overheads of instrumentation. We select two benchmarks. LULEF, this is a C++ application with very nice separation of communication and computation routines, but also many triple nested loop kernels. Then we select a second benchmark, which is MILK, a C application with a very deep and complex code base. We also, of course, evaluate the application with each application with 125 runs. So first, we begin with the cost results. So we provide the user with a table describing the parameter effect of the entire code base. So such as in this example, we simply provide the counts of loops and functions affected. In the third column, we provide the number of purely communication routines. So the ones that are MPI functions themselves, or they don't perform any computation, they just call MPI functions. And then we list all functions affected by the parameters, by given parameters. P is an implicit parameter due to presence of MPI. So this is always modeled, but immediately we see that from all other parameters, the parameter size is the one that occurs the most often. So for two parameter modeling, the selection of P and size parameters is actually the best choice in this here. And this helps the user, even if they want to perform a free parameter modeling, they already know, for example, which parameters have very little effect on the code base and should not be selected. The second important result, we show how we can make the instrumentation overheads less severe, which also means that experiments become cheaper and we can perform maybe larger modeling on the same compute budget. To do that, we evaluated LULEF without an instrumentation. This is our baseline. And then we evaluated 3 different choices of instrumentation and compared the overhead. So on the y-axis, we see the overhead given as a percentage. So evaluated our taint-based filter, which only instruments performance-relevant functions. We evaluated a default Scorpy behavior, and also one where we disable inlining and tell Scorpy explicitly to instrument all functions in the application. The distinction here is very important because default Scorpy filter performs an automatic inlining through the compiler plugin, which means that functions might be removed from consideration based only on compiler heuristic, and this is not a valid choice. This is not a valid choice for performance modeling. So the two choices are actually taint-based filter and the full program instrumentation, but we show the default behavior to show full a fair comparison. So first, for our taint-based filter, we noticed that the overheads are actually not so severe, up to 6% slowdown. It is quite similar for the default Scorpy filter, up to 20%. The additional overhead comes from the fact that, as we expected, the list of instrumented functions, there are many helper tools, helper functions, even some doing string manipulation that are instrumented by Scorpy, but in our instrumentation, they are considered completely constant time and not interesting. And finally, when we perform a full program instrumentation, here the results are very surprising. The application can get up to 45 times slower. And as we say, this is the only valid choice in addition to taint-based filtering. We noticed that there were many important computational kernels that were missed through from inlining in the default Scorpy filter. And they were, of course, present in the taint-based filter and the full program instrumentation. So clearly, we see that with our results, performing modeling becomes much cheaper, but also it might be possible to model the application on a range of parameters where it wouldn't be possible before because of excessive run times. When it comes to the quality of results, we first consider the effects of noise. So such as in this code example, we usually want to keep the influence only of parameters affecting the performance. But in practice, because of overfitting of black box models into noisy data, we might get false dependencies. We don't want to have models with false dependencies. Even if they have very low order of magnitude such constants, they still confuse the user. For LULEF, we observed that over 86% of the functions actually have constant runtime. And in the black box modeling, they would produce some models, many of them high complexity, very low constants, very confusing for the user. We remove those models automatically. Then we selected for all models, we selected top 5 most important complexity classes. So simply with the highest magnitudes and highest powers, highest exponents. And we noticed that with perf-taint, the user only has to analyze 14 functions, whereas to get to those same 5 classes, in the black box modeling, the user has to parse 33 functions. So it is much easier for the user to get to the most important results. Similarly, for milk, even more functions are constant. And here we have actually the white box result still produces many functions. But to analyze the black box results between those important functions, there are many of them that are simply have completely false models and they only add confusion. Similarly, we also want to remove the effects of instrumentation intrusion. So again, we only want to measure application behavior and not the effects of instrumentation. This can happen when the instrumentation overhead is excessive. To that end, we evaluated the modeling with full program instrumentation and also with our tainted instrumentation. And we found out that for one of milk kernels, the full program instrumentation produces an incorrect additive dependency between parameters p and size. Whereas for our instrumentation, we detect a multiplicative dependency. And this result has been confirmed, has been validated by a manual analytical modeling of the application. And finally, we use the results of our white box modeling to find out discrepancies where when it happens that the black box modeling actually shows strong dependencies with strong evidence in the data, but our results actually show that there should be no dependency whatsoever. One example was milk. When we scaled up milk by using more MPI ranks, we had many computational kernels where our analysis showed that there is absolutely no influence of the parameter p on the runtime of this function, but this function got slower when we increased the number of MPI ranks. We detected that the problem was dependence on the memory bandwidth in those functions. So when we added more MPI ranks on the same socket, at some point memory bus got saturated and the function got slower. To validate our findings, we perform a single parameter modeling experiments where we only vary the number of MPI ranks per node. So this is a single evaluation point of the LULEF. And we should see that the computational kernels their behavior should not change. There is no overallocation of cores. But surprisingly, we find that the entire application got over 30% slower, with some kernels getting 50% slower, simply when we allocate more ranks on the same socket. And we can only find that there is a problem with the experiment here, that the modeling doesn't actually model the application itself, only thanks to finding this discrepancy. Another second type of this result is we find a discrepancy in some MPI communication routines. And this happens because there's a qualitative change of the behavior of in the application. And this is something that cannot be handled very well by the modeling tool itself. And since we find that the models produced by the black models are better fit to the data, whereas our models with smaller degree of freedom actually produce worse models, we can detect that such behavior occurs. So to summarize, we detected important key challenges of performance modeling. We propose a new taint-based tool to mitigate those problems. And we showed that the entire modeling problem can become cheaper, it can produce better models, and we can validate the experiment design. Our code is available as open source on GitHub, and I would like to thank you very much for your attention.